I really like the things that we get to do in quarter 3 and the beginning of quarter 4. And so there's two things we're going to do today. One, I want to talk about your IA, and there's some pieces I want to go through. If you have it, if you are in a spot that you have any bit of it done, hopefully you're at a good spot where you feel like you're moving forward, you've taken data, you have a basic draft of what you're doing. I'm going to have you pull that up and we'll talk about that in a minute. You're not going to have to trade with anyone. This is all personal reflection, and I'm going to guide what I want you to look at. So we'll do that. And then the second thing we're going to do is we're going to start topic 7. And topic 7 is atomic and nuclear physics. And I just like it because we're at that edge of this that is the edge of stuff we don't talk about as much, or there's still so much work on figuring out the details of what's going on. And so I like it because it's at that place. We talk about gravity and it's like, well, at one point that was a really novel idea. And now it's just like, yeah, this is what we talk about. We talk about gravity. We know how it works. And so, down the line, this stuff will probably be more known and more just commonplace in what we talk about and understand. But right now, a lot of it is at a place that is still being figured out. There's a lot that we do know, and there's a lot that we're still figuring out. And so we'll be starting that. We do several different pieces on that. The thing can be daunting about it is you're like, we're going to talk about nuclear physics? That sounds crazy hard. The extent that it can go, oh goodness, yes. But the thing that's nice is it's kept in kind of bite-sized chunks that make sense. And if you can work through it and learn those pieces, most people find it to be functional and being able to move forward with it without too much trouble. So new ideas conceptually, sometimes you have to just go, okay, I don't know everything about it, but I can do this. And so that we'll keep working on that, and there'll be some good things that we get to do with that. So if you have your IA, I want you to take it out and just have it in front of you. And I'm going to walk through a few different questions. I'll post this later, but I want you to kind of have it in front of you and look for these things while I'm doing this. If there's something that I mentioned that you don't have, make sure that you just write yourself a note so you make sure you go back and do that. What this does is if you have all of these things, it allows me, your lab's probably going to be decently solid, and then it allows me to help get you from, here to here, as opposed to if you don't have these things, you're hanging down here, and I can't get you all the way up here on a discussion. So grab what you have if you have it. If you don't, then I would say, think about what you're doing, take notes as you need to. And like I said, I will post this list later. So here are the questions. First of all, as you went through your lab, and if you made changes and adjustments throughout, did you mention that? It doesn't need to be super long, but 1 to 2 sentences that says, hey, I started to do it this way. It wasn't working. And so I shifted it this way, and this is how it turned out. Those pieces bring out the personal engagement part of what you're doing. And so that can be really helpful in showing that and earning that 2 on the 0, 1, 2 for the personal engagement. Personal engagement doesn't necessarily mean that it lit your brain on fire. But if there is a connection, it's good to have that in there. But that connection alone is not going to get you the 2. The 2 is earned by saying like, yeah, it didn't work this way, so I did this. Or I needed to build this apparatus in order to do what I needed to do, so I built it like this. Or whatever it is that shows that you're thinking about this as you're going through it and not just writing things in the end for changes for next time. Are your variables and constants clearly defined? Do you have your usually it's really helpful if you have a section that just says independent variable. This is what I'm measuring. This is the unit that I'm using for that. And this is the range that I'm using. Dependent variable. This is what I'm measuring. This is the unit that I'm measuring. You may or may not have a range on that dependent variable because it's depending on on the range of your independent variable. And then your controls. What are you holding constant in what you're doing? And be particular with what you have. Saying something like, I dropped the ball from 1.5 meters every time is much more specific than I dropped the ball from the same height every time. So defining those to the best that you can, I kept a constant mass. Well, what was the constant mass? Stuff like that. Do you have appropriate background research? Background research should help the reader understand what you're doing, and it should help you arrange what you're doing for your procedure. And the readers then should be able to see the connection in that. So my background research says this, and because of what I'm seeing here, I'm going to set it up like that, having some connection within that. Your background research should be tied to what you're doing. You're not, unless it has a specific purpose, history of how it got there isn't going to be helpful. Names and dates are nice, they're fine, but it's not helpful in moving it forward. And so, again, they're not terrible things to have, but if you only have that, you're not going to be able to score well on your background research. Your background research should help the reader understand what you're doing and help kind of predict what outcome you should be getting. Data. Do you have enough data? For a solid IA, I know a lot of times there's sort of the minimum of 5 changes of independent variable and 3 trials. That is super bare minimum, and that on its own is not going to get you to score well on that unless there is some kind of binding circumstances that you can only do this. Time is not a binding circumstance. If you're like, well, if I just had more time, I could have done more. Okay, that's not one that's going to actually change anything. So shoot to 10, I'd say 10 to 12, depending on what it is. You may want to go up to 15 changes of independent variable. If you can measure it without too much change in things, if you're changing a distance, masses, stuff like that, then 10 to 12 is going to be a good amount of change for your independent variable. Trials, sometimes all you need is 3 trials. You always need 3 trials at least. Sometimes if they're all falling right within each other, if you have a static measurement, one that's not moving as you're trying to measure it, those should be pretty consistent. 3 trials should be just fine. If you have a measurement that you're trying to take while it's in motion, or while temperatures are changing, or while there's some change that's happening, then you'll want to take more than 3 trials. If your numbers are pretty consistent after 3 trials, you can just write that in there. My numbers were really consistent after 3 trials, so I'm choosing to only take 3 trials on this. Taking more trials isn't going to increase the consistency or show anything different on the lab. That's fine to do. But if your numbers are all over the place, taking some more trials to minimize that uncertainty in that can be helpful. It'll just tighten it up a little bit for you. Graphs. You need a raw data graph. If your raw data is not already linearized, you should linearize the graph. If your graph doesn't linearize, you try a couple of things, it doesn't linearize. What you can do is take and maybe pick 2 ways that you tried it and just put you can even put them side by side, just so the reader can see the progression of that graph as it's in an attempted linearization. And then you can go on and say, of the things, of the various ways that I attempted to linearize it, there wasn't something that came that would work for what I have. So I'm going to kind of dissect the graph that I have and then take a conceptual approach in justifying what the results are. But show that you have the ability to make those rearrangements and the thought process behind them. And so just kind of keep that in mind. If that's the case, we can talk about that and make sure that you're in the right direction. On your graphs, once you have your linearized graph, you need to have your, what if it doesn't need to be linearized? If it doesn't need to be linearized, if it's already linear, you just skip that part and you can just say my graph is linear and then continue on with what you have. And that's fine. That's actually a nice spot to be in. The part that you need to have is making sure that you have your uncertainties and your uncertainties represented with your error bars, and that you have your max min slopes both drawn on the graph and neatly calculated out so it can be followed and understood. And so whether you have to linearize your raw data first, or if your graph just appears as linear as you put it together, make sure that then you include your max min slopes and get all that on there. So one of the things that'll happen is you'll have an equation, and the equation will say maybe it's an x squared. So you would expect that you have an x squared relationship, and you go and linearize that, and it's not linear. Should you then go and continue to switch it? I would say no. I would say if you have a relationship and you linearize the graph in the way of that relationship, I'd keep it at that. Potentially it would fall within your error bars and could still be discussed as linear, but you're still relying and connecting with that relationship. It is a very, very, I'm not going to say impossible, but I'm going to say pretty close to impossible that someone would find an equation that's kind of a long-standing equation and have a result, like prove a different result, like you're changing the equation of physics. Pretty sure that's going to stay. And then you'd have to kind of justify your results within that. And so again, if it happens, talk to me about it. But don't try to, if it's not perfectly linear, but you can justify it within what you have or within that equation, I would say keep it as is for that. Conclusion, first of all, make sure you clearly state it. I can tell you that people will justify really, really well. They'll have lots of justifications and not state their conclusion. And so just because you did the calculations and you've shown different pieces doesn't mean that you've actually given a conclusion. So your conclusion should be the first part of that says, based on the information that I saw, this is what the relationship is from my independent to my dependent variable. And this is how it ties into what I did. And then move into your justification, and then move into your analysis of your lab. So keep that in mind, that you need to make sure that you clearly state your conclusion. Where was I? There we go. And then when you justifying it, if you can justify it mathematically, do that. If you can justify it mathematically, and there's a conceptual piece to that, do that too. Do both of them. Show that you know the math of it and you know the concept of it. Show both of those pieces. If it cannot be justified mathematically, then make sure that you have a very clear conceptual discussion of what you're doing. You can also take it so far as to using the graph that you have, making sure that your variables are in there instead of X and Y. So you're saying, well, the height of the drop and the height of the bounce are related in this way. And so if I were to continue this, it would act as it is with this graph and whatever. So you can kind of internally predict what might be happening further on, but then conceptually talk about what that analysis is. And so make sure it's nice and clear, make sure it makes sense. And then you can rely on that. Evaluation. Make sure you're discussing what went well and what might be improved. I did this lab. Here's all the pieces that I had. This went really well. I would do this again next time. This went really well. I would do this again next time. This provided some issue, and so I'm going to change it up a little bit. If I did this again, I would switch this or I would switch that and things like that. So the evaluation is both what went well and what didn't. And then with that, as you're adding in what might be improved, make sure that it's thoughtful and workable. Having some magic machine that is going to, do whatever is probably not going to be possible. But what could you do to tighten things up? If there's something that you notice during the lab, don't just wait for that to show in the improvement. Sometimes it's like, well, I'll just add it to the improvements that I should have done it differently. That's part of that personal engagement, that when you realize something should be done differently, if you have the capability to do it differently, that you actually just do it differently at that point. And so you go through and you talk about those things, talk about your improvements. Feel free to add that you did this at home, that your school, just even somewhere a line in there that says my school's on distance learning. It meant that we were doing that I completed this lab at home. In that, here's what went well, here's what didn't, here's what might have gone differently if I had been at school, here's what it went really well, even though I was at home. Whatever that is, just go ahead and put that in there. I think I also will put something in. I think there's a place for me to add that too, but it does help the reader understand that you had limitations beyond what you normally would. And then communication, make sure your data tables have your independent variable along the left-hand column and then your trials across the top. Make sure your numbers, even if it doesn't matter what order you collect the data, but when it's organized on your table, your independent variable should have the smallest number at the top and then keep going. So 10, 20, 30, 40, 50. Even if you collected them 50, 40, 30, 20, 10, you would still write them in your table as 10, 20, 30, 40, 50. And so you would have that nice and neat so that someone could look at the table and see some trends that are appearing there, even if they're not looking at the graph. Make sure that your data tables appear on a single page. So when you print, sometimes when you go and print your PDF to submit it, something shifts. And so if you print your PDF to submit it and you go back and you look and you see, oh, my data table, 5 pieces are up here and 6 pieces are down here. Well, that's not helpful, and that makes it difficult to follow. And so go back, shift that so that your data table is all on a single page. And then also make sure in the way of communication that you are using an equation editor type something to be able to show your equations. So you're writing them as they would look as an equation. You are not writing them in line like you're typing them. So make sure that an equation shows up as an equation. If you're showing a process, you should be able to kind of look at the page and have that process stand out and be able to clearly follow it. And then on your graphs, make sure that your axes are appropriately labeled, particularly if you're manipulating your graph. So make sure that if you're manipulating your graph to linearize it, your units will change usually on the x-axis. And so make sure that those are correctly represented. And then lastly, make sure that you're using the correct vocabulary. We talked about this when we talked about resistance and resistivity. And again, that's the sort of thing that on a rough draft, I can usually pull out and be like, I don't think this is what you meant here. But make sure that you are just being thoughtful in the vocabulary that you use and that you're using the correct terminology, particularly when there's words that are close. If you're talking about power, don't talk about work. If you're talking about work, if you're talking about work, it shouldn't be measured in watts, stuff like that. So those are the main things that I wanted to have you think about and work through. And I'll put that list up on Schoology. I'll put it in the IA folder so you can look at that. But those are some of the biggest pieces that I find as I'm looking at these that are ones that can be taken care of ahead of the other details. And so sometimes I get a rough draft and I look at it and I'm like, they flipped their variables and this isn't going to work. So those are some big things. They graphed it this way instead of that way. And the relationship that they're making is inverse of what they had or whatever it is. And so some of those big picture things, trade, if you have a friend who's in the class and you can trade with them and just say, hey, can you take a look at this and see if there's anything that doesn't make sense? That's really helpful before I take a look at it. So over the next couple of weeks, I'll put up, I'm going to send out a Calendly later today that when you are ready for your one-on-one, for your rough draft overview, that you can sign up on that so we can get that taken care of. The biggest thing is I want you to be able to meet with me before you submit it. And so I was just going to do it next week. I'm going to do it over the next couple weeks. And so different people are at different spots. And I'll get, I had in my mind, I had a date due set up, and I think I'm going to push that back a little bit. So there were some talks about what Q3 would look like, and it's looking more normal than I had anticipated. So I can shift those things a little bit. Any big questions before we go on?
Do you want us to submit our rough draft to you before we meet with you so that you
Yes,
can
sorry.
look at it?
Yep. And so when you sign up, what you'll do is you'll sign up, and I'll put this in there too, that you'll sign up for the meeting, and you'll email me your rough draft. And so then I can take a look at your rough draft and we can talk about it in that way before you submit your final draft. Yep, thank you. Any other questions? All right, let's talk about nuclear physics. We have 22 minutes. All right, nuclear physics there's a few mind shifts that we'll have to kind of take from pieces that you would learn in chemistry to how this applies in a nuclear situation. When we're talking about nuclear physics, we're talking about a single atom and how that single atom behaves in different situations. When we talk about nuclear physics, when you talk about chemistry, in chemistry, you like hammer in protons never change, the atom never changes, it's always the electrons, it's always something with the neutrons, but the protons never change. Well, in nuclear physics, the protons change. Woohoo! And so, not always, sometimes it's just an isotope situation, but the protons do change, and then we also are dealing with energy from that change. And so a couple of things, I'm going to go ahead and share my screen with you, and I'm going to go back and forth on a couple things here. Pull up this, pin that, the PowerPoint up. Nope, not that one. It's on the other computer. Cool. I will not go back and forth on things today. All right. So the first thing to think about, and the first thing to keep in mind, is that with our nuclear structure, we have protons, we have neutrons, and we have electrons. Protons have a positive charge, neutrons have no charge, and electrons have a negative charge. And when we have our nucleus, we have our protons plus our neutrons, and then electrons are in electron cloud. And they're found in rings around, or like energy levels around the nucleus. And those energy levels we'll talk about in a little bit for what we're doing. The way we're going to represent this is something like this. So if this is our element X, we're going to have that today. And we'll have our A number and our Z number. And the A number is going to be our atomic mass. Say mass number. And a difference here is that when you're talking about the periodic table and you talk about your atomic mass, you're talking about the idea that you have, like if you took a random scoop of that element, it would have a certain percentage of the different isotopes. And so that atomic mass then is going to be based on that, on all of those isotopes combined in there. What happens with this is we're talking about a single atom. And so this is actually just, it's going to be how many protons and neutrons we have. So protons plus neutrons. And it is very specific for that single atom that we're talking about. It's not a mix of different isotopes. We know exactly what isotope it is based on the number of protons and neutrons that we have. And then the Z number is the number of protons. And so you'll see these, all, in all kinds of situations. So it might look like this. U-235. U is uranium, has 92 protons. And so then, this isotope of it has 235. There's some vocabulary that you're going to get in here. And when we're talking about protons and neutrons, we call them nucleons. Nucleons essentially are any particles that are found in the nucleus. And so when we talk about uranium here, we would say it has 92 protons and it has 235 nucleons. Nucleons just mean it's found in the nucleus, so it's protons and neutrons. So if we needed to find the number of neutrons, we would just take the 235 minus the 92, and we would have 143, I think. So when we're looking at this, you'll see this as we go along. And this week we're focusing on two things. We're focusing just on the understanding of nuclear equations, and then on just like how to write them and balance them and know what your outcome is. And then we're also focusing on the energy released as we're looking at the shift of electrons. And so we'll talk about that in a minute. So I'm going to take this down in a moment. So if you want to take a screenshot of that, do that. I've got everything on there. I'm going to erase this. And then we'll talk about nuclear equations. And you'll do some practice with this week. I still need to put up the assignment. I shifted it from last year, so there's a couple of adjustments I still need to make. And I'll get that up today so you can work on it this weekend if you choose. It's going to be cold. It's going to be real cold. So stay in and do some nuclear physics. Equations might look something like this. So let's say you have U-235, like we just had, 92, and that's uranium. And let's say it's going to be bombarded with a neutron. So neutron will write like this. It doesn't have any protons with it, but it has one nucleon. And so because there's no protons, it is assumed that then this nucleon is a neutron. And when that U-235 is bombarded with a neutron here, you end up with U-236, still U here. And so anytime you're looking at nuclear equations, your nucleon numbers on each side will balance out. So 235 plus 1 is 236. It's equal on both sides. 92, 92. You didn't have a change on that. So your top numbers always add up to be the same. Your bottom numbers always add up to be the same. And so this week you'll do some practice on those. I'll do a couple others here. We're going to take thorium. You're going to get real familiar with some of the parts of the periodic table that you haven't done much with before. This we'll talk about radioactive decay next week, but this is an alpha decay. And here you've got 228 and then 88. And so if you have 232 to 228 and you need to predict what's going on for this one, you would know that, well, this side would have to equal 232. So there would be a 4 here because 228 plus 4 would give you 232. 88 plus 2 gives you 90. And then you would look at a periodic table and say, okay, well, 2, second element on the periodic table is helium. And so you'd be able to identify what you have there. This could work in something like this, where you have two elements that are colliding here. Just putting these, in any of these situations, just putting these, like just putting a uranium atom and a neutron together isn't going to do it. It's got to be at really, really high speeds, certain kind of characteristics surrounding what's going on in order for this to happen. It's not as straightforward as a chemical reaction would be. But let's say we have beryllium and helium, and they collide, and they give us carbon-12. And if we want to figure out what else is there, 9 plus 4 is 13. So 12 plus 1 is 13. 4 plus 2 is 6. Carbon has 6, so that's already balanced. We have a 0 here, which would give us a neutron that would be left over. I'm going to mess with you just for a second because it's fun to think about. We'll talk about this a lot more later. You might also have something like this. You have tritium. It's a hydrogen 3. It's one of the heavy hydrogens. And it is going to go into helium 3. And it's like, okay, well, the 3s make sense. Oh, hold on. How do we get a 2 over here if we only had a 1 here? We get, actually, we put a -1 here. It is released as an electron. And actually what happens here is that one of the neutrons turns into a proton. We will talk about that more later, but this is the kind of bizarre stuff that we get to work with here. So this week you'll be doing some practice on these and working through some of the ideas of what's happening in how these work. I'm going to erase that in a moment. You will never have to predict the whole right side. So you'll always have something that you can relate it to. I'll never give you like, beryllium plus helium in a nuclear reaction, what's going to happen, and just leave it blank. So you won't have to predict what will occur. You'll just have to be able to identify, based on something that's in there, what else would be occurring with it. When we talk about decay, next week you'll need to be able to take and say, like, read it and understand what is being said and be able to write it. But again, you won't ever have to be like, I wonder what's going to happen if, uranium and I don't know, whatever, pick a situation. You won't ever have to blindly predict that. All right. The other thing, and we're going to, on Tuesday when we meet, I'm going to give you enough stuff right now to hopefully be able to get started and get going on the practice problems. And then on Tuesday when we meet, I'll take questions on those, but I'll take about half of the time for some questions and about half of the time to kind of wrap up kind of some of the big pictures of these. And I'll be putting some videos up probably this afternoon that can help break down some of this. But we know in general, we'll talk about some of the details of this, of how we got there on Tuesday. But we know in general that we have our nucleus and then we have these energy rings that the electrons are in that are going around there. And what happens is when you have energy added into here, these electrons can jump levels and they can go to, it's called an excited state. And so when you add energy, these electrons can go to an excited state and they can jump out here, and they have higher energy present. Get that arrow in there better. What then can happen is if they're in a higher energy and they drop down, they release energy. And they release energy in the way, in both of these, it'll be an electromagnetic wave. Photon. So if you've ever had glow in the dark stuff, you think about something that's glow in the dark, just like the little stars that go on your ceiling or a glow in the dark t-shirt or something like that. What happens with that is you have to have it underneath the light. And as it is underneath the light, it is adding energy. That glow thing is taking in some of the energy from the light of the sun, and it is exciting those electrons to another level. When you turn off the light, those electrons are released. Those electrons drop back to a lower level, and the energy is released in the form of a photon. And in the case of a glow-in-the-dark object, that photon is in the range of visible light. So if you think about glowing things, it's almost always the same color. It's because it's the same energy drop every single time for that material. And so what we can do is we can look at how these go. And depending on what wavelength is released, we can actually figure out how much energy is released with that wavelength. So I'm going to take this off. So if you need a screenshot that, do that. And you do this, you'll see some diagrams that look like this. Okay, and your diagram might look like this. And I'm going to put some numbers over here. I've got uh, 0.85. This one is for hydrogen, and I'm using it in electron volts. Sometimes they're written with a negative, sometimes they're not. When you're looking at a transition, if you're going down, you're losing energy, and if you're going up, you're adding energy. So if I'm going from here to here, I would have to add a certain amount of energy in order to get up from negative 13 to 340. If I'm going from here to here, I'm losing a certain more amount of energy as I'm dropping from here to here. And so sometimes you'll see that as negatives. Sometimes you'll see it as positives. Sometimes you'll see it as positives reversed. But know that the biggest thing is you're looking at the change in energy every time. And so you think about the electrons can be all of these different places. Here's your ground state. And then here is your first excited state. And so if it goes from here to here, so think about the glowing item. You put some light on it, and it causes it to go from here to here. You turn off the lights, and it comes down. It comes back down, releasing that energy that it already took in. And you can go any of these different connections. So let's say they're in excited states. It can drop from here to here. It can drop from there to there. It can drop from there to there. Any combination you can do. You can drop from here to here, whatever. And so depending on that, you'll have a release of energy in each situation. Well, this release of energy can be used with something called Planck's constant. And so the equation that we'll use with this is, get the right pieces in here. You have E, the energy released, is equal to H times the frequency of that light. And so if you can measure the frequency of the electromagnetic wave, sometimes it's in the visible spectrum, sometimes it's ultraviolet, sometimes it's going to be in the UV or infrared. It could be in either one of those. It could be farther out. But as you do this, we have this number called Planck's constant. And Planck's constant is 6.63 times 10 to the negative 34th joules times seconds. And so you'll use that in combination of what's going on. Now you'll notice that you have joules here. Up here you have electron volts. And so remember when we talked about that? So if we have an electron volt, it's an electron times a volt. So it ends up being 1.60 times 10 to the negative 19th coulombs times, remember, a volt is joules per coulomb. So electron volts. Well, the coulombs cancel out here. So 1 electron volt equals 1.60 times 10 to the negative 19th joules. And so that ends up being an important conversion that you'll need to get through for each one. I didn't get anywhere near as far as I wanted to. I'm going to let you go ahead and take a picture of this. And screenshot the bottom part if you'd like. And I'll talk about what our plan is, because we only have 3 minutes left. So plan is this. This concept is kind of goofy to get your brain around, but once you get going on the practice of it, it starts to make some sense. And so what I'm going to do is I'm going to post this afternoon, I'm going to post a bunch of videos. One that walks through exactly what you're doing with this. One that I'll post this video that we're doing right now that'll show you the how to do the equations of it, and I'll get your practice problems up there to get going on. Then next week, so this will still be due next Thursday, and we'll quiz on it next Thursday. I'll take questions on it on Tuesday, and I'll go into, there's some atomic theory of kind of the discovery of the atom that we need to take a look at, as well as an experiment that and we need to discuss. And so we'll go through those pieces. I'll go through a little bit more of this on Tuesday, and then I'll take questions. Even though we haven't gotten through everything, I think once you get going on it, you're going to be in okay shape if you watch the other video I put up. And then B, we're at an okay. I chunked it up differently than I would in a normal year. And so we're doing less in this week than we normally would. And I think it's attainable to still do by next Thursday. So those are the things that we have. Have fun thinking about nuclear physics. If anyone starts like giving you grief about something, you can be like, I'm sorry, I'm studying nuclear physics. I'm brilliant. So you can just use that with people this weekend and or over the next several weeks. And then I'm excited to be going through this stuff with you all. So have an awesome week. I'll hang on if you have any other questions. Have a great weekend. Happy Friday. And we'll keep moving forward. So I'll be on for a couple more minutes if you have any other questions. Other than that, have an excellent day. We'll see y'all later. Bye-bye.